That's correct. I'm going to be busy those days. Oh, we've started. Welcome back to ECE 501B. We have homework number 4 due on the 20th of October, which I believe is a Thursday, and that's supposed to be on that date, and it's the traditional 11:59 p.m. schedule. Today what I want to do, as promised last time, is begin with Chapter 6. And now we're going to be talking, Chapter 6 is talking about inner products. And we just keep adding more and more structure to these concepts. We started with vectors, then we started talking about dimension and linearly independent and span. Now we can then we started talking about operators. Once we had operators, we could start talking about eigenvalues and eigenvectors. Now we want to put some more structure onto these concepts, and the next one is going to be inner product, and that allows us now to speak a little bit more effectively relative to length and angle. Now we can define those topics with respect to vectors. And so we'll give the concept, the properties, then we will create something with more structure than a vector space, and that's an inner product space, which is a vector space with an inner product. And the idea here is really keep thinking about extending this beyond just tall, thin vectors. Now you could be dealing with polynomials. You could be dealing with infinite dimensional ideas eventually in terms of orthogonality. Pythagorean theorem, you've probably learned that a long, long time ago, a squared plus b squared equals c squared, but now we will see it in terms of these finite dimensional, and then you can think in terms of what this might be in functional analysis. Orthogonal decomposition, the Cauchy-Schwarz inequality, and the triangle inequality, all of those now are provided to us because we will develop this concept of an inner product. Once we have an inner product, we'll be able to talk about orthogonality, which leads naturally then into this Pythagorean theorem. So let's look at inner product spaces, which is Chapter 6. And this is now going to provide our vector space. Let's say we just pull out a vector space. Now we have a vector space with the concepts of both length and angle. Or another way of thinking of that could be, now we could talk about distance when we're talking about vectors, and maybe the closeness of two vectors or multiple vectors if we now are talking about angles. What angular separation is there between these two vectors? And in order to do that, we need this concept called an inner product, and let's now provide the definition, or what you could think of as the rule that is creating this new structure on top of our vector space. And that new structure is this inner product. The inner product between two vectors, and let's just denote those as v and w. They both are in the vector space that we're living in, which is, let's say, capital V. The inner product between two vectors, v and w, is written as this bracket v comma w close bracket. That's not parentheses, it's now brackets, so that we can distinguish between just a list of vectors and this inner product. once we have that bracket notation, we can say that an inner product is in fact a rule that takes an ordered pair of vectors, and again, that ordered pair we could call is this list VW, and it creates actually a scalar, which that's why we're doing the bracket VW, and that's now an element of our field. Complex or real, depending on what the field is underlying our vector space. So we are developing this rule that takes an ordered pair of vectors, VW, and the order is important, V comma W, and creating a scalar. In order to do that, we want this rule to actually satisfy or possess certain properties, and now we'll list those properties. So this inner product is taking two vectors into a scalar and has the following properties. One is the property of positivity. It's always nice to be positive, so we're giving this inner product a positive attitude. Now, we're dealing with positivity, which means that if you take the inner product of a vector with itself, that's going to be greater than or equal to 0 for all V, an element of the vector space. We also want a property called definiteness, which says that if we take the inner product of a vector with itself and we actually get the scalar 0, then that's only going to happen if and only if the vector that we started with was the 0 vector in our underlying vector space. So we have positivity, definiteness. We also want then another property called additivity in the first slot. Remember, this pair of vectors is an ordered pair. And now if we had two vectors added together in the first slot and ordered with, or inner product with a third vector W, then we can say, oh, that's equivalent to U bracket UW plus bracket VW. And that's true for all vectors U, V, and W belonging to our vector space. So we have additivity in the first slot. We also want homogeneity in the first slot. That means then that if we scale the vector V in the first slot and inner product that with W, then that A actually slides out of the inner product, the scalar, and we can now say that that's the same as A inner product, or times the inner product of V comma W, and that's true for all scalars and all vectors V and W in our vector space V. Yes? So now the question was, what does it mean if we say a complex number is greater than 0? In this particular case, and I think the book says that if you have a complex, or if you have this symbol greater than or equal to 0, then we're actually saying that that number is real and it's positive. No. Inner products are not only real and positive, but remember what this positivity is. This is a vector of v with itself. So you can have an inner product that gives you a negative number. It could give you a complex number, an inner product of u and v. But here, u and v are both v. It's v with v. So now if you have j and j, whatever those vectors are, these are now vectors. But now if you have j and j, this is going to determine how we perform the inner product. And so we'll find that we want the first coordinate, or the first vector, each of their coordinates multiplied by the other coordinates conjugate. So that if you now have j and j, you have j times j star, and so now you have a real positive number. So now the greater than or equal to 0 says that we're talking about a real positive value. But that's when v is repeated. That's what we're meaning by positivity. The vector is with itself. So in this case, you would say if v was a 2 vector, you would say v1 times v1 conjugate plus v2 times v2 conjugate, and that's now the inner product. But we haven't gotten there yet. We're just giving the properties of the inner product. We want the inner product to satisfy that, and basically by your question, you've now demonstrated that we need, when we're dealing with complex vectors, we have to do some kind of conjugation in the definition of our inner product, which is why the inner product is going to have this conjugation part to it. So we have one more property. We have positivity, definiteness. It can only equal 0 if the vector is the 0 vector. We have additivity in the first slot. We have homogeneity in the first slot. And then we have a property called conjugate symmetry. And by that, we mean that if we have two vectors and we form their inner product, then we want that by this property. We want the inner product to satisfy this property. We're saying that if we flipped the order of the elements in our inner product and made that W with V, then we're saying that that's going to equal the complex conjugate. And that's what I'm trying to indicate by this star. It's a pretty ugly star, but hopefully you won't have to see it in the sky. You can just create your own on your own paper that looks a little better than mine. But that's the complex conjugate, and this conjugate symmetry is true for all V and W in our vector space. One comment to make is that the textbook uses an overbar for complex conjugate. And so when you're looking in the book, maybe I don't want you to get confused. So I will try to use this star notation for the conjugate. And if we're dealing with vectors that are real or over the field of real numbers, then we don't really need to worry about that complex conjugate. Note that conjugate symmetry simplifies if our vector space V is a real vector space. And now we can talk about what we really want in Chapter 6, and that is what we will call an inner product space. And that is a vector space let's say V, souped up or with an additional property, and that's with an inner product, or the vector space V plus an inner product. And the inner product is really a rule, plus an inner product rule on that vector space V. If we have a vector space and we have an inner product rule on that vector space, we'll just say we have an inner product space. And let's look at an example. Which I've already verbally introduced, but let's formally do that. If we're now in an n-dimensional space, f to the n, with an inner product, then if we take v1, v2, now these are the coordinates of my vector v. There's v, and we have the coordinates of the vector w. We are going to then create our standard inner product to be, we pair up each coordinate and we form their product by taking the first vector and multiplying it by the conjugate of the first coordinate of the second vector. And then we add to that the product of the second coordinate of the first vector times the conjugate, complex conjugate, of the second coordinate of the second vector. And we have this pairwise product of the first vector and the second vector's coordinate conjugated. And this actually looks like what you're used to seeing for a Euclidean inner product. This is the Euclidean inner product. And if we look at that with the above rule, then if you look at the inner product of V with itself, then that's actually going to be the same as taking the 2 norm of V and squaring it. And you could think of that as the squared Euclidean length of the underlying vector that we picked, V. So just think in terms of 2-dimensional or 3-dimensional. If V was 2-dimensional, you would have V1, V2, and W1, W2, but if you just wanted to look at the length or the norm of V, you would say V1 times V1 conjugate plus V2 times V2 conjugate, and now you get the magnitude of V1 squared plus the magnitude of V2 squared. That's coming out of your inner product, and that's actually the square of the Euclidean distance, or the Euclidean length of that vector V, with components V1 and V2. And if we specialized our field or restricted our field or our vector space to be real, then if we looked at the inner product of U, so we have bracket U comma V, close bracket, that's actually just the inner product of the vectors U and V, or inner product, the dot product. the inner product is the dot product when we're dealing with the real vector space. And this is the standard. Behavior we expect from geometric vector spaces. Now let's look at some other types of inner products. Now that we have this notion of worrying about multiplication of coordinates of vectors, we can talk of another inner product on f sub n even. So other inner products are possible. Let's say that we have another one on the n-dimensional vector space, f to the n, where now maybe we say we have a vector v inner product with w. We could define an inner product to be c1 v1 w1 conjugate plus c sub 2 v2 w2 conjugate on up to c sub n v sub n w sub n conjugate. And to be a correct inner product, or for it to satisfy the properties of an inner product, we need these c sub i's to all be positive real numbers. That's an inner product on f to the n. Let's look at some more interesting maybe vector spaces. Let's say that we now wanted to look at inner product on this mth order polynomial vector space. One such inner product, let's say, is a bracket p comma q. P and q are both vectors in this m order polynomial vector space. We could take the integral from 0 to 1 of p of x times the complex conjugate of q of x dx. That could be a legitimate, that now satisfies the properties of our inner product rule. There aren't really that many reasons behind the limits on the integration. We now have polynomials that we haven't necessarily put any restrictions on, but now we are using this finite interval. I'm not sure that it may matter for your application, but in terms of the inner product, this is just sort of a nice set of endpoints for your integral, 0 to 1. But it could be minus 1 to 1, or it could be minus 10 to 10. That's still okay. Another possible inner product, let's now restrict it to P2, just so that we don't have to go on. And in this one it has, we can draw some of these polynomial representations. Now the inner product, let's say, of v with w could be defined by taking the polynomial v that's second order and evaluating it at the point x minus 1 and multiplying that times w, and I forgot to put my r. I was doing a p, but that should have been r. So now I don't have to conjugate my second vector's coordinates, plus, let's say, v at 0 times w of 0 plus v of 1 times w of 1. So let's look at an example of that, and it's actually very important that I picked 3 unique points to form this chain or this summation when I'm living on a second order polynomial or dealing with a second order. So keep that in mind. But now let's just look at an example. Suppose that somebody gives us v of t is t plus 1, and that's in the set or in the vector space of second order polynomials. And let's say that our vector w of t is t squared minus 1. And let's go ahead and use that most recent inner product that we just defined. Inner product number 2. Then we can look at v of minus 1. What's that equal to? That's 0. What's v of 0? That's 1. And what's v of 1? That's 2. And now let's do the same evaluations at the same points anyway for our polynomial w. Now, what's w evaluate to when w is evaluated at minus 1 for t? That one's 0. W of 0, that's minus 1. And w of 1, 0. And now we have those 6 points, we can form the inner product, which is inner product number 2. We can say v comma w inner product. We now take v of minus 1, which is 0, times w of minus 1, which is 0, plus v of 0 times w of 0, plus v of 1 times w of 1, which is 0. And what's the inner product of the polynomial or the vector v with the vector w in the second order polynomial vector space? It's now minus 1. So we know the inner product doesn't have to be positive from this example. Now, what I said before was this point that, or I tried to make a point of it, we needed 3 values, or you could think of sampling that polynomial at 3 different points. In this second order real polynomial to define a valid inner product. Or if we were dealing in or living in a vector space of P4, we would need to sample the vectors at 5 or more values, and then take the inner product of those 5 values. And the reason for that is so that we don't violate one of the inner product properties. Meaning we could have the inner product of V with itself equaling 0 without V actually equaling 0 if we didn't sample a sufficient number of points based on the order of our polynomial. As an example, suppose we have V living on this, or being a vector in this second order real polynomial vector space, and suppose that somebody says, oh, I want to propose the following inner product. I want the inner product to be V of minus 1, W of minus 1, plus V of 1, W of 1. Now, all we really have to do is come up with one counterexample to violate one of the properties of our inner product, and we would know that that's not a valid inner product. In this case, suppose that we picked V of t equal to t squared minus 1. And that's in P sub 2. And I hope it's clear that that's not the 0 vector in that vector space. Yet, if we look at this, what happens when we look at this potential inner product applied to V itself? Then we have V of minus 1, which actually before this was our W, wasn't it? So we have V of minus 1 is 0, and V of 1 is 0. So here we have 0 times 0. That's V of minus 1 times V of minus 1, plus 0 times 0, which is V of 1, V of 1. And that's 0, and V wasn't 0. So this actually is that particular 2-point inner product on P2 is not valid. And if you wanted to sort of think of this in terms of a graphical, here's T, then you can hopefully see what this quadratic looks like in this plane. What's V at 0? It's minus 1. And what's V at 1? And what's V at minus 1? So we have something like this. This is now our V of t, and we can find a polynomial, a second order polynomial that goes through 2 points that evaluate to 0, and that's going to cause us to violate our inner product. And if you had something in P3, now it could possibly go through the horizontal axis 3 times, and you could pick those particular values in your inner product, and you could say, oh, that's not going to work. You need more than 3. So here we need more than 2 points to evaluate, and then we would have the ability to not have a 0 inner product when our vector v was not the 0 vector. Meaning now we could pick v at, well, in the previous example, I think we picked v of 0, didn't we? And so now we could have picked any other point. We could have picked v at minus 2, and we would still be okay. Now, let's look at one of the other inner products that we have defined. But that example was supposed to illustrate this connection between if we are starting to be designing inner products on a polynomial, real polynomial space, that was supposed to justify why we need one more sort of sample than we have order of our polynomial. If we have a quadratic, we need 3 points. If we had a cubic, we need 4 points. If we have a fifth order polynomial, we need at least 6. Otherwise, we could find a polynomial and points that would violate our inner product rule. Or we could basically show that we can find a non-zero vector that produces an inner product of 0, and that's not what we want for our inner product. So let's look at inner product 1, and let's now say that v of t is t plus 1, and let's say that w of t is t squared minus 1. With the first inner product that we defined on this space, we now said that, oh, that's this integral from 0 to 1 of t plus 1 t squared minus 1 dt. And we can now form that multiplication, and we have t cubed minus t plus t squared minus 1 dt. And we can integrate polynomials pretty easily. That's convenient, so that we now have the integral of t cubed, that's 1/4 t to the 4th, minus 1/2 t squared, plus 1/3 t cubed minus t. And we will evaluate that at 0 and 1, which means the lower limit we don't need to worry about. Those all evaluate to 0, and we have 1/4 minus 1/2 plus 1/3 minus 1. Or if we sort of pair those up to just, we now have minus 1/4 and we have minus 2/3, so that the inner product of v with w is now minus 1/4 minus 2/3, which is, if we get a common denominator, we have minus 3 and a minus 8 or minus 11 over 12 for the inner product using inner product number 1. And what was the inner product of v and w using inner product number 2? This one gave us minus 11/12. The earlier one gave us minus 1. So we can have different values for the inner product, but these aren't too far away, are they? Even using quite different structures for the inner product. But we use the same vectors, v and w. We got minus 1 for the second one, inner product, and we obtained close to minus 1 for the second. Yes? No. So the question was, is it necessary for the order of the polynomial to pass through the x-axis that many times? You can find a polynomial in that space that will do that, but each one doesn't have to. For example, if you had a quadratic, what happens when you have complex roots? Does it ever go through x? No. So you could just shift that curve that we had done before up or down. Let's shift it up, and then we don't go through x. So there are ways that you can not necessarily find sort of real zeros in this real polynomial vector space. You can create real polynomials that do not have all real roots. But when they do, then you're going to have them going through. So you could have a third order polynomial that crosses once. Okay. So let's look at some other characteristics or qualities of inner products, or what we can do with inner products. Let's notice the fact that the first slot in our inner product definition exhibits additivity. We had first slot additivity, or additivity of the first slot. Notice that first slot exhibits additivity and homogeneity. And that's consistent with a linear particular, or a linear map. So notice that the first slot exhibits additivity and homogeneity. Thus, if we fixed a vector, let's say W, then this inner product, V with W, is a linear map from our vector space V into the scalars. Our inner product takes us from our vector space into the scalars. Now if you just fix W, now you can pick any vector you want in your vector space, and you can show that this inner product gives you a linear map. You're fixing W. So if you needed a linear map that takes you from your vector down to the scalars, this would be one way to build such a linear map, is to use this definition of inner product. Let's look at some other characteristics of inner product. And now let's look at what happens with respect to the second slot. We can also prove certain properties about the second slot. And the first one that we can prove is that actually we have additivity of the second slot. Meaning if we start now with the inner product of U with the sum of V and W, right now we don't know how to play with an addition in the second slot, but we do know how to play with an addition in the first slot. And so we maybe want this sum to shift from the second slot to the first slot, and how can we do that with the rule that we know? We can take the complex conjugate of that, and that allows us now to interchange the order of our vectors. Meaning now we can say, well, that's equal to the first slot being filled with the sum, V plus W, and inner product with U, but that's only true if we now take the complex conjugate of that inner product. Is that okay? That was one of our properties of the inner product. But now we can look at using additivity of our first slot. Since now the sum is in our first slot, we can say, oh, we can now push that or use that, so we have V inner product with U plus W inner product with U, and we now need to take the inner product of that sum. But the sum of an inner, or the sum of the conjugate of a sum is the sum of the conjugates, which says now that we have V comma U inner product conjugate plus W inner product U somewhere. And maybe I won't work over there anymore. And we'll just try to be patient somehow. Whoa. Wow. So much for today's lecture. I will fill it in later. So, let's say that we now have whatever we started with. We started with u, comma, v, and w, and we wanted to look at the additivity of the second slot. And we had looked at now shifting all of that, and I think we'd ended up with then v, comma, u, inner product, plus w, comma, u, and conjugate. And what happens if we now conjugate those inner products? U, comma, v plus u, comma, w, and isn't that what we were wanting to show? We now have additivity of the second slot. So we can now sort of distribute those summations either in the first slot or the second slot. We have additivity of either the first or the second slot, and we can use that to our advantage. The other property of the second slot is actually conjugate homogeneity. By that, then, we have a vector u, and let's say that we scale the vector in the second slot by a. Well, we don't know how to pull that second slot scaled vector, how to separate that out, but we know how to switch positions of our vectors in the inner product. We can move that second vector to the first slot, and we can move the first vector, or the vector in the first slot, to the second slot by the conjugate. But we now know how to deal with a scaled first vector or first slot. What did we say we had relative to the first slot? We have this homogeneity of our first slot. So let's now say that we have A pulled out of that inner product because we have homogeneity of the first slot, and now we can conjugate the product, or we now have A star u, comma, v, and that now shows that we have conjugate homogeneity of the second slot. So if you have something in the second slot scaled, you can pull that scalar out, but you have to conjugate it. We just demonstrated that. Let's look at some norms. We've discussed various norms. Before, and not all of these norms play nicely with inner products. To sort of minimize that not playing nicely from here on out, we're going to define the norm as the following. We're going to just go ahead and say that the norm of a vector v is the square root of the inner product of v with itself. And we know, based on this being the inner product of v with itself and the way we're conjugating things, it's going to be real, so we can take the square root and not end up with problems. It's going to be positive. What did I say? Real? We want it to be, it's going to be positive. Real and positive with our inner product that we've defined. Well, we're actually going to just use this. So here, note that if v comma v is the Euclidean inner product, then this is equivalent to our earlier definition of the two norm. However, we'll use this norm definition of taking the square root of the inner product with any inner product. And one thing that we can see is that if we look at a scaled vector and we look at the square of the norm of that vector, you can then show that that's going to be the absolute value of that scalar squared times the original vector's norm squared. Using the properties of the inner product that we've demonstrated or introduced. Question? So now we're really sort of changing the definition of these 1 norm, 2 norm, 3 norm. We're just saying, if we say we want the norm, let's just find our inner product and take the square root. We're not really worrying about the L1 or the L3, any of those kind of norms right now. We're just saying, if we're playing with different inner products, we will allow those inner products to produce a norm based on this definition. So whatever we pick for an inner product, the norm is going to fall out based on just taking the square root of that inner product. Now that we have that, now that we have this concept of inner product, we can actually start talking about orthogonality. And now we will say that two vectors, let's say v and w, in our vector space V are orthogonal if this inner product V with W gives us 0. And this relationship, inner product of V and W, now we don't really need to worry so much about the order of W and V. We can also say this also implies that if we looked at the inner product of W and V, that will also give us 0. So there's our definition of orthogonality. We just have to have an inner product and then find two vectors that give us an inner product of 0, and those two vectors are now, by that inner product, orthogonal. And here are a couple of observations. Relative to orthogonality, and really sort of this concept of 0 vector, or the additive identity. So now 0 is orthogonal. The 0 vector is orthogonal to every vector. So if you have the 0 vector in your vector space and you put it into your inner product with another vector, you're going to get 0 out. So that 0 vector in your vector space is orthogonal to every other vector in your vector space. Also, 0, the 0 vector, is the only vector that is orthogonal to itself, which is good. We don't want a vector to be giving us a 0 for an inner product when it's non-zero. So 0 is the only vector that is orthogonal to itself. Let's look at an example. Suppose now we're in this second order polynomial over the reals, and let's say that our inner product of V and W is in fact going to be V of minus 1, W of minus 1, plus V of 0, W of 0, plus V of 1, W of 1. And that, I think, was our second definition of an inner product over polynomials. And it's important that we have 3 samples if we're dealing with P2. What we want to do in this example is find a vector W, find a W that is orthogonal using this inner product with this inner product and it's orthogonal to, let's say, V of t equal to t plus 1. So now we want to find a or some second order polynomials that are orthogonal to t plus 1 using the inner product number 2 that we've defined. Solution. Suppose we now just create a generic second order polynomial for W. Let's let W of t be some scalar alpha times t squared plus another scalar beta times t plus another scalar gamma. And that's a generic second order polynomial. We want to find alpha, beta, and gamma such that V and W are orthogonal. And in this case, we can start evaluating what W is for those 3 sample locations on the x-axis. What's W of minus 1? And again, we haven't yet defined alpha, beta, and gamma. We're hoping to be able to do that, to force orthogonality. If we evaluate W at minus 1, what do we end up with? Alpha minus beta plus gamma. What if we plug in 0 for t? First two go away and we get gamma, and now if we plug in 1 for t, we have alpha plus beta plus gamma. And we can recall what V was at those 3 sample locations. V of minus 1 is 0, V of 0 is 1, and V of 1 is 2. For orthogonality, what do we need? Relative to the inner product. By definition of orthogonality, we need that inner product to give us 0. And that inner product says, oh, take V of minus 1, which is 0, and multiply it by alpha minus beta plus gamma. Take V of 0, which is 1, and multiply that by W of 0, which is gamma. And take V of 1, which is 2, and multiply that by alpha plus beta plus gamma, and that's supposed to equal 0. Or we end up with 2 alpha plus 2 beta plus 3 gamma needs to equal 0 in order for orthogonality of V and W. So now we have one equation and 3 unknowns. So a lot of W's that are orthogonal to that V is what this is saying. Is that clear? What if we look at some? Many possibilities. For example, suppose we start by letting alpha equal 0. Now we're just going to look at linear W's, aren't we? Since alpha was the scalar on t squared. If we let alpha equal 0, now we want 2 beta plus 3 gamma to equal 0. And again, we have one equation and 2 unknowns. Suppose we let gamma equal 2. Then beta is minus 3. And now we have one such vector, second order polynomial, we'll say W sub 1, which is equal to beta times t minus 3 times t plus gamma, and that is orthogonal to V of t equal to t plus 1 with the chosen inner product that we started with, which was inner product number 2 in our polynomial vector space. What if we did a different choice? Suppose we said, let's let gamma equal 0. Now we have 2 alpha plus 2 beta plus 3 times 0 is equal to 0. Or now we have alpha plus beta is equal to 0. Or we have alpha is equal to minus beta. And now we could just let one of those be 1. Suppose we let alpha be 1. Beta is now minus 1. And we've now found a second vector, w sub 2, which is now alpha was 1, and that was the weighting or the scalar on our quadratic. So we now have t squared minus 1 times t, or we have t times t minus 1. And this vector, w sub 2, is also orthogonal to v of t equaling t plus 1. And we could check this if we wanted to. V of minus 1, that's now 0. V of 0 is 1, and V of 1 is 2. And now we still have W up there, so we have W of minus 1 is so we square minus 1 and we get 1 minus a minus 1. So is that 2? Okay. This is very high math, but it's a good thing you bought that calculator. I'm glad you should have brought that to class today. If you went to the bookstore and bought a calculator, we need to use it, justify it. So we now have W of 0. We have 0 times 0 minus 1. That's 0. And W of 1, we have 1 times 1 minus 1. That's also 0. So that now if we look at the inner product of V with W2, now we have 0 times 2 plus 1 times 0 plus 2 times 0, and we get what we wanted, orthogonality of W sub 2 with V. Now that we have this concept of orthogonality, we can move on. We can really grow. We can expand our horizons to where now we can do a squared plus b squared equals c squared. We can now solve Pythagorean relationship. So now we have Pythagorean theorem. But now we're doing it in general with generic vector spaces. We have the Pythagorean theorem, and that's theorem 13 in the book. And that says that if we have two vectors, u and v, and they are orthogonal, in our vector space capital V, then if we take the norm of their sum and square it, that's going to be the same as taking the square of the norm of u plus the square of the norm of v. And we can now prove that, knowing what we know about norms and inner products and orthogonality. And our assumption in this theorem is that u and v are orthogonal. But we can rewrite this norm squared in the form of an inner product. We now have the inner product of u plus v with itself. And we can clean this up a little bit. We can use additivity of the first slot And that now allows us to say that we have u inner product with u plus v plus v inner product with u plus v. And what else do we know? Well, now we have this sum in the second slot, but we just showed earlier that we have additivity of the second slot. So we can do that again for both of these pieces. Here is our second slot additivity. And that allows us now to say that we have u inner product with u plus u inner product with v plus v inner product with u plus v inner product with v. So that these two came from that, and these two came from that. But what do we know about these two inner products of the four? The second inner product, u with v, what was our assumption in our theorem? Those are orthogonal, and we now know what orthogonality means. That means that that's 0, and this piece is also 0, and we're left with the two pieces that we wanted, meaning now we have the result that we have on the right-hand side. We have the inner product of u with itself plus the inner product of v with itself, but those we can write as the norm of u squared and the norm of v squared. And that's what we were trying to show, that the norm squared of u plus v is equal to the norm squared of u plus the norm squared of v. And how much of the inner product, or definition of the inner product, did we have to pull up or to use? Did we have to define anything about the inner product or specify which inner product we were using? No. So now we can use any inner product we want and apply the Pythagorean theorem. This result did not depend on the inner product. It just depended on orthogonality. And now what we want to do is we want to start looking at other ways that we can take advantage of orthogonality. Now we've seen that we've created a theorem, but another way that we can now use that is to decompose vectors using orthogonal decomposition. And maybe before I even get too far into that, let me just sort of say that we might have this vector v and another vector u. We now want to decompose u into a component that lies along v. Let's say that this is now AV, and another component that's actually orthogonal to v. So that now we want to be able to do this orthogonal decomposition when we have two different vectors. And we'll pick up at that point on Monday.